Good morning and welcome to the late breaking news for Friday, October 3rd. Today's presentation on Phoenix Mars Lander, the first 90 days in the Mars Arctic, is presented as a team presentation. We'll have a central presenter, but I wanted to point out before that began that in this forum it's important to have engineering competence standing by as well as the science. As a result, Robert Shotwell of the Jet Propulsion Laboratory is in the front row and available for comment after. He was a systems engineer for the Phoenix project from proposal through landing plus 10 days. And then it looked like everything was okay and he left. He was a senior systems engineer for Outer Planets roadmap studies and microsatellite efforts at JPL, the lead for the Xenon ion feed system and engine integration and test for Deep Space One. He did propulsion system design and test engineer for Mars Pathfinder, a great place to get involved with the Mars program. He's an MS in astronautics from the University of Southern California. As a Stanford guy, we have another name for that. And a BS in aerospace engineering from Texas A&M University with over 15 years of experience at JPL. He's currently the program engineer for Advanced Optical Systems program at JPL. So Robert's in the front row and available for any press inquiries that might come up. I'm John Rummel. I'm from NASA headquarters. 3 weeks ago, I went to East Carolina University as a director for an Institute for Coastal Science and Policy, so I'm an uninvolved, innocent bystander in some respect. But for the Phoenix mission, I was the planetary protection officer to start and approved the ability of Phoenix to use its arm to dig into the unknown soils of the northern polar regions. But this is a science presentation, and to present today on the science of Phoenix is Dr. Victoria Hipkin. She's got a bachelor's in science in physics from the University of Edinburgh, so she comes locally, and a master's in science in remote sensing and image processing. Her PhD was jointly with University of Leeds and the British Antarctic Survey, looking at extreme low temperature events, which seems appropriate, over an Antarctic ice shelf, the first 10 meters. Well, she's gone a long way after that. Her postdoc in New Zealand looked at acoustic radar remote sensing of the atmosphere, and then she went to the University of Toronto to research Mars mission concepts. She went to the Canadian Space Agency thereafter. I always like to think of it for fun and profit, but I've worked in government, so I'm not sure that's the case. And is the program scientist there for Planetary Exploration and was the Met mission scientist on Phoenix. Vicki has also been one of the 3 science leads for the mission since it landed successfully in May. Vicki?
So we're going straight into a short movie here, just to share with you what it was like to actually...
Atmospheric entry on my mark. 5,
So this is the
4,
Operations Center at the
3,
Jet Propulsion Laboratory.
2, 1, mark.
And here we have animation
Expected
showing
peak heating rate in 1 minute and 40 seconds. Standing by for a possible platinum blackout. Phoenix now 1 minute past the entry point. We still have a signal by Odyssey. At this point in time, Phoenix goes normally through peak heating.
This was the moment we've been waiting for after
Phoenix now 2 minutes and 25 seconds past the entry point. We still have a signal by Odyssey. Standing by for reacquisition by direct to Earth.
An Arctic lander on Mars.
Stop of Odyssey canister data and switch to 32K in 10 seconds. Standing by for expected parachute deployment. Parachute deployment trigger detected. Heat
So
shield
many
trigger
critical
detected.
systems that must
Ground
function
velocity
during
90 meters per
entry,
second.
descent, and landing. As we reached each of the moments, we had a cheer in the
Land leg
operations
deployment
center.
trigger detected. Ground velocity 60 meters per second. Standing by for altitude conversion. At this point in time, Phoenix would have normally reached altitude convergence. We're standing by for confirmation via telemetry. Radar reliable. Altitude 2,000 meters. Altitude convergence detected. Altitude 1,800 meters, 1,700 meters, 1,600 meters. Standing by for landing separation, altitude 1,100 meters. Signal may drop out during landing separation. altitude 1,000 meters. The separation detected. We have verified the signal. Gravity turn detected. Altitude 600 meters, 500 meters, 400 meters, 250 meters.
So this was a direct feed of information via the Mars
100
Odyssey
meters,
satellite.
80 meters, 50 meters. Come on. Constant velocity phase detected. Altitude 40 meters, 30 meters.
And as we heard that it slowed down enough.
20 meters, 50 meters, standing by for touchdown.
We knew we were going to land safely.
Touchdown signal detected. Landed it. Landing lead sequence initiated. Helium vent detected.
This was a very moving moment for the whole team, and it still moves me now. Principal investigator Peter Smith, who just saw, and the first deployment are solar panels. And here we've also deployed the biobarrier on the robot arm on this mission. And this was the success we were looking for. This really showed that we touched ground and our solar panels had opened so that we would actually have power to continue with our mission. So the engineering team did an absolutely incredible job. We landed beautifully and surprisingly aligned east-west with our solar panels as well. And in exactly the place we wanted to be, in the Mars Arctic, in some polygonal terrain, which is indicative of there being ice just below the surface. So now I'm just going to go through a presentation of what we actually did on landing. This is very much focused on the science and what was happening at the University of Arizona's Operations Center in Tucson, where we were all based for the first 90 sols of the mission. So to commemorate landing, the students in the Operations Center actually produced this postcard. And the Mars letters here were made up of our first day's landing images, showing the footpad and the camera and the solar panel deployment. And you can actually download this from the University of Arizona's website, which I'll give you at the end of the talk. So we were landing in the high Arctic of Mars to confirm a discovery that had been made by Mars Odyssey orbiter in 2001 from the gamma ray spectrometer instrument, which had detected large amounts of hydrogen subsurface, which was rather a surprise at the time. So we were landing to confirm that there was indeed big deposits of ice just under the surface. And as I said, this first picture that we got back of this wonderful hillocky landscape, which, as I said, is very characteristic of Arctic icy terrains, was a very good starting point for us indeed. We also landed on May 25th, which happened to be in northern summer, just going into northern summer of Mars, and we landed just north of the Arctic Circle in Mars. And for relevance to science, this was important seasonal time to arrive, as it corresponded to the time that the North Polar ice cap started to sublimate into the atmosphere in the summer season. And this is driving some of the current weather and climate on Mars, is the annual freezing and sublimation of both carbon dioxide ice and water vapor ice from the polar caps. So the plot you see at the bottom is showing the expected water vapor developing over season. We were expecting to see more water vapor coming past our landing site as the mission progressed. So as the first Arctic explorer on Mars, all the other missions really went to near equatorial sites, with the exception of Viking 2, which went to about 45 degrees north. We were there to answer some big questions about habitability and current and past climate. The first 6 sols or so were involved in payload deployment. So here you see the Phoenix payload. We had a surface stereo imager, which was giving us information that would both support atmospheric studies and also geology and documenting everything we did, essentially. We also had a Canadian weather station, which involved the first LiDAR to operate from a planetary surface, and a MET mast. This was in collaboration with both Finland and Denmark. I then had analytical instruments looking at mineralogy and chemistry, the microscopy, electrochemistry, and conductivity analyzer, MECA. It was built in JPL. And with its associated package, the TECP, the Thermal and Electrical Conductivity Probe, which was actually on the robotic arm. And then TIGA, the Thermal Evolved Gas Analyzer, was our main instrument for trying to detect organics and look at composition. And this was something built at the University of Arizona. We then had the robotic arm, also from JPL, and the robotic arm camera, which was a contribution from Germany. So while the weather instruments actually were switched on Sol 1, and we started collecting continuous pressure and temperature data immediately, for the analytical instruments, we really had quite a big job to go in figuring out what our samples would be that we would deliver. And what you see here at the top of the slide is the map of our workspace, the area accessible to our robotic arm that was produced in the first few days. And we'd actually designated a national park area that we weren't going to touch and collect samples from until we practiced a little bit with the robotic arm first. The second picture, as you go down, just shows where some of our first trenches were, and I'll talk more about those. So there's the Dodo Goldilocks trench on the left of the image, and there's a Snow White on the right. And at the bottom, we see some of our first images coming back from Mars. So on the left there, we see the touch test from the robotic arm, and this looks rather like a footprint. So it was named Yeti by us. And then on the right, you can see an animation made of images taken on successive days. And this is the Dodo Goldilocks trench. And what was very interesting to us is, the first trench we dug in the soil discovered some white stuff, and we actually saw that disappear, essentially sublimate into the atmosphere over a few days. And our initial hypothesis was that it could have been ice or it could have been salts, but with that sublimation, we really thought that we had made the confirmation we were looking for, and we'd had landed in a place where we were a few centimeters from sitting on top of ice. So I'm going to skip now to Sol 27 and talk a little bit about our first sample deliveries. And here we have samples that were delivered to our wet chemistry lab on the MECA instrument. And what we were looking at is to get a soil profile, so to get a surface sample and a depth sample, and understand the soil properties here for looking for elements that would be needed for habitability, and looking just to understand what the soil properties were here. So rosy red was our surface sample, and sorceress was our ice boundary. And I hadn't said before that our principal investigator, Peter Smith, had adopted a naming convention where we were using fairy tale names to help us identify targets in our rock and soil workspace. So you see on the right, you see the robotic arm actually delivering some sample to the optical microscope, which is part of the MECA package. And we have at the bottom there some results from optical microscopy. And this is showing that the soil was mainly a reddish color and very fine particles. And the roundness, when we looked at them in more detail, was indicative of them being windblown, being of aeolian origin. There were also some other colored particles in there, both dark particles and some that looked white or optically transparent. And work is ongoing to analyze exactly what we've seen there. So here we have a nice animation which shows how the wet chemistry lab operates. So we have the delivery now into the cells. What happens first is we've actually brought with us a liquid reagent, mostly water. And the first thing we do is thaw that, and then we deliver it into the little cells which have ion-sensitive electrodes therein. And we deliver a little pill of reagents. And then you'll see in a moment this mechanism opens to deliver our soil sample, which has come in through the grill, you can see on the upper left there. And it delivers it into the cell, and we have a stirrer which stirs for some time, and we add some more reagents. And from that, each of the little ion-sensitive electrodes is sensitive to a different anion. And this has been the source of the discovery of perchlorate that's been publicized from this mission. We also have discovered that the pH of these soils is alkaline, which is actually quite different from the Mars Exploration Rover environment. And we've also have not seen any sulfates. So where we are in the Arctic does turn out to be different from where it's been explored before. We've found some very small trace amounts of other salts as well. So following this, I'm going to talk now about the efforts we went to deliver an icy sample to the Thermal Evolved Gas Analyzer instrument. On the left here, you can see a sequence of images that really show the robotic arm has been scraping and preparing this trench. Initially, we tried to collect samples simply by scraping, but the ice layer here is very hard. I mean, ice can have the tensile strength of concrete. And we had brought with us a rasping tool, a small drill bit, essentially, that would allow us to drill down into the ice. And you can see a pattern of 16 holes in the middle of that image. And that gave us enough material to actually deliver. And to practice our deliveries, we did have a test bed at the operations center in Tucson, and you can see an image of us preparing the rasping activities in that test bed before actually commanding on Mars. Acquiring an icy sample for TIGA turned out to be a very big challenge. The properties of the Mars soil were rather unexpected to us. So we got our first scoopful and tried to deliver it. It was called Glass Slipper. And we tried to deliver it, and it simply stuck in the scoop. We'd collected it early in the morning, and we had a lot of trouble figuring out how to get a sample of this icy, sticky soil into our instruments, and had many attempts. And the bottom picture here shows we had media coverage. A documentary team would come in each day that we thought we were going to actually succeed in delivering this icy sample, and would be there to register the joy on our faces and our disappointment as well. But we persisted, and eventually on Sol 64, we delivered a sample called Wicked Witch into the Thermal Evolved Gas Analyzer. So here again, we have an animation to show how this particular instrument worked. The white pill you see here represents the soil. Very small amounts of soil are actually needed in this analysis. So we have it disappear into an oven, this probe, which is heated up to very high temperature. The TIGA oven can go in steps from 0 up to 1,000 degrees Celsius. And we can choose those steps to select for the different compounds we're looking for. And in this sample, we did actually formally detect water vapor in the low temperature ramp. So temperatures below 35 Celsius, we did detect water vapor in the mass spectrometer. So this is a formal analytical identification of water from the surface of Mars. Though our desire has really been to measure the hydrogen to deuterium ratio, which we're trying to get a larger sample into TIGA to do that with high accuracy. But it was also this sample that gave us an indication that we are actually seeing carbonates on Mars. Small amounts again, I don't have a volume for you, but the evidence for this was a carbon dioxide detection at temperatures greater than 200 degrees Celsius. And there was also an endotherm that we saw that would have been consistent with calcite. So at the moment, we're tentatively identifying some of the composition of our sample to be calcium carbonate. And this work is ongoing, and full analysis will be presented later this year at the American Geophysical Union Conference in December. At the same time, the surface stereo imager has been taking images of our entire workspace looking up to the horizon. And this is the compilation, which was finally finished around Sol 63. This was our mission success pan, or named by ourselves, Peter Pan, again after our principal investigator. You can see a picture of the surface stereo camera below there. But this was really quite remarkable. This was more than 100 different pointing directions of the camera that were compiled into this image. And it does allow you to zoom in quite high resolution. And we could look at some of the rocks around us, and we found both flat, platey-looking rocks and rocks with big vesicles in them. And we're trying to figure out whether our geological context is actually representative of this whole Arctic region, or whether there's something special about us landing on the ejecta of a fairly recent crater, Heimdall. On Sol 65, we had a picture taken of the Phoenix science team against a mural that had been painted on the outside of the Tucson University of Arizona Operations Center. So there were about 100 of us there, and we were actually all living on Mars time until Sol 90. And the Mars day is around 40 minutes longer than Earth, so this actually had us changing shifts to work sometimes during the night and sometimes during the day, and a very interesting experience that was too. Sol 80 saw the first frosts, so now we were heading out of the middle of summer, and you can see a surface stereo imager of the frosty soil in the top left there. And on the right you can see the meteorological mast and the telltale sensor, which was our very simple sensor to measure wind. This was a very late addition to the mission. Certainly, the meteorologists, myself on the team, were very keen to have a wind measurement, and it was simply a bob on a line where we could measure the deflection by looking in this mirror. But what I want to draw your attention to are the sparkles that you can see on the mirror at the bottom of that animation now, and we were actually seeing ice crystals forming as the time passed. As you can see, our local time was essentially the middle of the night, though at this point the sun had not quite yet dropped below the horizon at that time. It was just very low in the sky. Sol 90 was the end of the primary mission, and actually Sol 86 was the first time that the sun did drop below the horizon. And I've actually mislabeled this. This is a sunrise image from Sol 90 taken with the surface stereo imager. But by the end of the primary mission, this is what our workspace looked like. We had a number of different trenches, and we delivered 3 samples to our wet chemistry lab out of 4 possible cells that we had with us. And we delivered 4 samples to the thermal evolved gas analyzer. So we still had a lot of interesting sampling that could be done in the extended mission, which NASA kindly granted us. So we're now in the extended mission. We're around Sol 127, I believe, today. And winter's approaching. And this is when I show the weather results from the mission, because during the first 50 or 60 sols, we were really pretty sunny and calm all the time. There was not so much to report. And here you can see the minimum temperature of the day plotted against the Sol number. And you can see around 50, we went through the summer equinox. We had the highest temperatures then, and since that time, we've been steadily falling. But it was really after Sol 75, Sol 78, that we started to see a lot more in the way of cloud around the landing site and some ground fogs as well. One of the very interesting things for me, as I was involved in the Canadian experiment, the Canadian MET package, was getting results that really exceeded our expectations from this instrument. So a LiDAR is an active remote sensing instrument which sends light pulses up into the atmosphere, which reflects off the particles that are there. So when the atmosphere is very clear and not dusty, you don't see much. But when we have cloud and dust events, then we get a very, very good high resolution, 5-meter vertical resolution up to 20 kilometers image of atmospheric structure. And what this image shows, I'm sorry I haven't been able to get this animation to work, but the surface stereo imager was actually able to image the LiDAR beam on Mars. And you could see it sparkle if the animation would play, and that was just the individual particles were reflecting light back into the camera. The results that came from the LiDAR, they've been getting more and more interesting as time goes on, as the weather is developing and we're seeing more activity. I think I forgot to say as well that when we started to see frost, it wasn't really because temperatures were falling, it was because we were seeing a big change in the amount of water vapor meeting the site from the sublimation of the polar cap. So the clouds that were forming now were really because we were actually seeing that water vapor transport past our site. What this image shows is clouds seen at an altitude of around 4 kilometers. But what was very special here were these things that have been labeled as fall streaks. Here we're seeing crystals of water ice that are actually falling through the atmosphere. And it's very characteristic that they have this shape sheared by lower level winds as they fall. And so this is our first detection of falling snow on Mars. And this is quite significant too, because until this point there hasn't been any direct confirmation of precipitation on Mars, certainly in terms of water vapor and water ice. And this means that the way that the water transforms from the atmosphere to the surface can be both precipitation and condensation. So it was a very exciting and very recent result. This was a press event on Monday. So we're now getting to the end of the mission, and just to explain how final that can be for this particular mission, this is a plot of the hours of sunlight available per sol over time. And we're currently on the descending part of this yellow line. You can see where we are right now is the little green dash. And this is really, since Sol 90, the sun has been going below the horizon, and it will be doing that more and more. And our operating day will be getting shorter, and we'll have less and less power available to do the intensive activities, such as the robotic arm excavations. But around February, we expect to see carbon dioxide ice starting to condense around the lander. And carbon dioxide ice has a condensation temperature of around minus 140 Celsius. So this is not going to be good for the lander's batteries. And we're also expecting to see rather significant volumes of this form around the lander, perhaps up to a meter or so of deposition on top of our solar panels. So it's not looking good for the batteries to survive that winter period, and the fragility of our solar panels too is in question. But I believe the engineering team will make a manful effort to actually recontact our lander in the springtime again, but without much expectation that that will really be possible. So I'm just going to leave you now with websites so that you can continue to follow the mission. You can get daily updates from the University of Arizona website. And here our image data is actually streaming directly onto the website. You will see it there as soon as the science team does. And then in Canada, we're producing daily weather reports, or as near to daily as we can, given the downlink being irregular. And this is an example of the weather report for Sol 112. We have a max and minimum temperature reported, and we have symbols that represent here frost on the right and dust devils on the left. So we've started seeing dust devils on Mars too. So I'm just going to stop there, and I thank you all for turning up this early in the morning on the very last day, and very much appreciate having this opportunity to share my excitement about the mission with you.
Thank you. I think we have time for one or two questions. If one can go to the microphones. Thank you.
Hi, yeah, Mark Bentley, Austrian Academy of Sciences. Fascinating results. I wondered, you didn't talk about any of the AFM data at all. I've only seen calibration in one particle, and I just wondered if there were other data available, and if so, when we might see them. Thank you.
Okay, I believe that the AFM data was featured in the press release on Monday. There's been some very interesting results there, and the AFM is the atomic force microscope. It's also a new type of instrument to be deployed on a planetary mission, and that's been a contribution from Switzerland. And this is allowing us to see very tiny submicron-sized particles, and we've seen different types of particles there. We've seen rounded particles, which are again consistent with aeolian activity. We've also seen very interesting Pleiade particles, and this was the basis of an announcement that we may be seeing phyllosilicates on Mars. It's actually the Pleiade particles that we've been seeing with the atomic force microscope. So thank you for the question.
We have time for one more question.
Malcolm Smith, British Interplanetary Society. Can you tell me if there's any plans to send the flight spare to the South Pole?
That would be lovely. I don't believe we have a flight spare to send, but I think there's been interest from the scientific community to compare the poles. They are very different. It's a very asymmetric planet in that way. So I know the scientific community would be very interested in one day seeing a mission go to the southern pole as well.
Let's thank Vicki again and stand by for the plenary.